In Chapter 19, we will be looking at lipids. One of the lipids you may be familiar with is in chocolate, and that is in cocoa butter, which contains lots of triacylglycerols that contribute to its wonderful flavor. Lipids are biomolecules that are soluble in organic solvents and insoluble in water. They are defined by their physical properties and not their functional groups. There are many nonpolar carbon-carbon or carbon-hydrogen bonds, so they have few polar bonds in different functional groups. And the word lipid comes from Greek lipos for fat. So we have a couple of the polar esters, but for the most part it's nonpolar compounds. Lipids that you may see here include the triacylglycerol from oils, and those have ester functional groups. So there's 3 esters present, and those come from these long fatty acid chains, these carbon-carbon chains, and we even see a couple of alkenes here. Another lipid we might encounter is cholesterol. The hydroxyl OH is in blue, so that's our functional group there, but again, there's a lot of carbon-carbon and carbon-hydrogen nonpolar bonds. And then we have vitamin E that can come from spinach leaves, and we have another hydroxyl group here and also an ether. And these are all compounds that are water insoluble. And here are a couple of different lipids that we've already seen prior to this chapter. That includes vitamin A, different fatty acids, oral contraceptives, margarine and butter, aspirin and prostaglandins, soap, and then olestra, which we saw in the ester chapter. Lipids are hydrolyzable. This means that they can be converted into smaller molecules by hydrolysis with water. And remember, in Chapter 17, we used water to hydrolyze esters and amides back to carboxylic acids. So it broke them into smaller molecules, and there's different categories of lipids that can be hydrolyzed. One of them is different types of waxes. We have triacylglycerols and phospholipids. So if you remember this ester, we break this bond after the addition of water, and we'll get a carboxylic acid plus the alcohol. We also have some lipids that are non-hydrolyzable, which means they can't be cleaved into smaller units with water. These tend to be more varied in structure. So in the last slide, we had the waxes, triacylglycerols, and phospholipids. Those all contain ester bonds. And in these non-hydrolyzable ones, we have very different carbon skeletons. We'll see that soon, but some of these include steroids, fat-soluble vitamins like vitamin E, and then also eicosanoids. Lipids will release 9 kcals per gram, so they're an excellent source of energy. That means that for 1 gram of fat, that is equal to 9 calories if you're looking at dietary labels. They're also a key component of the cell membrane. They serve as chemical messengers and can be a protective coating. Fatty acids are carboxylic acids that have long carbon chains of 12 to 20 carbons. This one happens to be palmitic acid, which has a carbon chain of 16 and 2 oxygens. This is the polar part of the molecule, and because it's polar, this part likes water, so it's hydrophilic. And then this part here, all these long carbon chains that are made from nonpolar bonds, this is the nonpolar hydrophobic region. So that does not like water. We have two types of fatty acids. There's the saturated fatty acids, which has no carbon-carbon double bonds in the long chain. And an unsaturated fatty acid has one or more carbon-carbon double bond, and it's usually cis. So that's the naturally occurring one. So stearic acid is an example of a saturated one. So we can see here there's no carbon-carbon double bonds in the long chain, and oleic acid is an unsaturated one. And we have this cis double bond here. And here's a table of different common fatty acids, which you will not need to memorize. But we can see in the top half, those are our saturated fatty acids, and they contain 0 double bonds, and they have increasing melting points as you increase the number of carbons. So lauric acid has 12 carbons, it has a melting point of 44, while arachidic acid has a melting point of 77 degrees Celsius with its chain of 20 carbons. So these are all solid at room temp, and room temperature is usually about 25 degrees Celsius. As we add double bonds to the unsaturated fatty acids, that decreases the melting point. Arachidonic acid has 4 double bonds, and the melting point is negative 49, so these are all liquid at room temp. So if you think of vegetable oil, that's going to be an unsaturated fatty acid, and that is liquid at room temperature versus something like butter, which is mostly made of saturated fatty acids, and that tends to be solid at room temperature. As the number of our double bonds increases, our melting point decreases. And in a fatty acid, when you have cis double bonds, these do not pack well. So the more carbon-carbon double bonds you have, the lower your melting point. So you can try to imagine stacking a whole bunch of these molecules. They do not stack well. No stacking, no packing, lower melting points. You might have heard of omega fatty acids. The N indicates where the carbon is at the first double bond, beginning from the CH3 end. And omega-3 fatty acids, which is shown here, that carbon double bond starts at 3. These have health benefits for those with heart disease. We may have also heard of the omega-6 fatty acids or even omega-9. And that just means that the first double bond with the omega-6 starts at carbon 6. So we're going to draw a skeletal structure of gadolinic acid, which has the condensed structure there. It's a 20 carbon fatty acid chain from fish oil. So I'm going to start with my carboxylic acid. And then here we have CH2 So 1, 2, 3, 4, 5, 6, 7. I have a carbon-carbon double bond. And it's usually cis, and here there's CH2s. There's 9 of those. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a CH3. So if I go back and double check my CH2s, there's 7 of those. So there's 1, 2, 3, 4, 5, 6, 7. I have a CH double bonded to a CH in the cis conformation, and then 9 CH2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the CH3. B is asking us to label the hydrophobic and hydrophilic. The carboxylic acid is the hydrophilic, which is the water-loving part. And then this part is the hydrophobic. It's so nonpolar. How its melting point compares to the arachidic acid, which is 77. This one is a saturated fatty acid. And then this one, arachidonic acid, has a double bond, but if we look carefully, there's 4 of them. So that one has 4 double bonds, it's negative 49. So this one should be in between. And it's probably going to be closer to arachidic acid because there's only 1 double bond there. Waxes are defined as being esters that are made from fatty acids and a high molecular weight to alcohol. So the general structure of a wax just looks like an ester, but what makes it a wax is that it has long carbon chains. So if we're doing this wax here, you find your water when we go to form esters. And then you form it to this OR prime, which makes the ester or wax. And in actual structures, you still find your water but now we just have a longer carbon. So you can either draw this out or you can leave it in the condensed form. And then my O will have CH215, CH3. So this is cetyl palmitate, which you don't need to know the name of. This is a major component of spermaceti wax. And when commercial whaling was commonplace eons ago, the spermaceti wax was obtained from sperm whales and was used extensively in cosmetics and candles. Waxes are hydrophobic, as you may be aware of. They can form protective coating on feathers of birds to make them water repellent. They can also prevent water evaporation on leaves so the water can maintain the water inside and keep extra water outside. We'll see waxes in lanolin wool coat fibers of sheep, and beeswax contains a special kind of wax as well as 200 other different compounds. So this is the wax that's present in beeswax, this myricil palmitate, and you can see how long the carbon chain here. So this is the hydrophobic region, and this is the hydrophobic region. Waxes can be hydrolyzed just like esters can, because that's pretty much what the functional group is. And in the process, we break this CO bond, and then we're going to form the fatty acid, OH here, plus the alcohol. So we'll get back the fatty acid and the alcohol. Triacylglycerols, or triglycerides, are triesters made from glycerol and 3 molecules of fatty acids. Glycerol is the same thing as propane triol. And we can make this by joining these together. So we're going to remove our water, just like we would in any other ester reaction, but now we're going to do it 3 times. And our product, so I have my 3 carbons with the O's, and I'm going to bond them to these. And your R groups here can be the same or they can be different. So this is a triacylglycerol. And sometimes they use a box to kind of draw things out so you can see what these are made of. So this is glycerol, and that's bonded to fatty acids. So this is what they call a block diagram. So you can have simple triacylglycerols where all of these are the same, where all of the R groups are the same, or you can have a mixed one where one of the carbon chains is unsaturated. When we're looking at general features of the different triacylglycerols and fats, you can see kind of the composition of each of these different fats that we consume in our diets. Butter has a large concentration of saturated fat, which is why this one is a solid at room temperature. As is coconut oil, a lot of time there's a lot more saturated fats here. And that one does not contain a lot of unsaturated fat, whereas butter does. Shortening is mostly unsaturated fat, and it has some of the saturated fat, which makes it very spreadable. And then olive oil is mostly unsaturated fat. It has a little bit of saturated fat, which is why it can solidify if you put it in the refrigerator. Canola is mostly unsaturated, so these ones are the ones that are liquid at room temperature. And then we have vegetable oil margarine, which is the stuff that's kind of like, I can't believe it's not butter. It's made up of all of the different types of fats. And that one contains also trans fats, which are not healthy fats. And these are formed when triacylglycerols are partially hydrogenated. So they've gone and reduced some of the double bonds to make them more like saturated fats. More saturated fats come from animals. So this is a saturated triacylglycerol. So they come from animal products and they have higher melting points because they can pack together. And then more of the unsaturated fats come from plant products. So there's one unsaturated one here, but it's made up of also the saturated. And these one come from plant products, like I mentioned. They have lower melting points because they don't pack together as well. Palm and coconut oils are high in saturated fats, and diets that are high in saturated fats can lead to heart disease. So oils from fish are rich in polyunsaturated triacylglycerols. These fish oils contain a lot of omega-3 fatty acids, which are very good for your health, and it's good for those that are at risk of developing coronary artery disease. When we draw triacylglycerols, this is kind of like when we drew esters. So if you remember when we did esters, we had a carboxylic acid plus some alcohol. We would find the water and then remove the water and squeeze those two together to form the ester. So we're doing the same thing here. Our carboxylic acids are the fatty acids. So this part is the carboxylic acid, and then we have 3 of them. So we're just forming a triester. We're going to look for the water in each of these and then squeeze those out. So here's the H from my alcohol. So I'm going to do that 3 times. And then it tells us here the oleic acid is the group in blue, and then stearic acid is the group in red. So when we draw the product of this, I'm going to have the glycerol part in red here. And glycerol is the same thing as propane triol. This is the new bond that I formed to each of the fatty acids. There's the carbonyl. I have 1, 2, 3, 4, 5, 6, 7. And then a cis double bond, and then 8 carbons. So 1, 2, 3, 4, 5, 6, 7. Here's the next one. And then the last one here. So that's the triacylglycerol that we formed. Or triester. So unlike many fats and oils, cocoa butter is used to make chocolate and is remarkably uniform in composition. All triacylglycerols contain oleic acid, which is esterified to the secondary alcohol in the group of glycerol, and either palmitic or stearic acid can be esterified to the primary alcohol groups. So draw the structure of a possible triacylglycerol that composes cocoa butter. Glycerol is our trialcohol, or our triol. And it's telling us that the oleic acid, this one goes to the secondary alcohol, which is this guy right here. And then we can fit stearic acid or palmitic, so I just drew stearic acid here, is esterified to the primary alcohol groups. So we can have it with 1 stearic and then 2 oleic acids. So these are the C double bond OH groups. And that is the same here. So we'll have 2 oleic acids. And you can either draw it out or just do the same thing here. So CH2 So I find my water. And if you wanted to draw it out in the skeletal form like we did in the last slide, you can definitely do that. I think that might be quicker actually than running these out. If you have a diet that is largely made up of fats, this can be a very harmful diet. You really want to aim for 20 to 30% of your calorie intake from fats. And these can come in many sources. Some fats are required in the diet because they are the building blocks of your cell membranes, and your stored body fat insulates an organism. And this stored body fat insulates us and other organisms, and we can use this energy source later. So it is important to have those in there. Saturated fat stimulates cholesterol synthesis in liver. And then if you have too high of cholesterol, this leads to plaque on arteries, which can narrow your blood vessels, resulting in a heart attack or stroke. Unsaturated fat lowers the risk of heart disease, and this decreases cholesterol in the blood. And omega-3 fatty acids reduce the risk of a heart attack. So people that are having high cholesterol are often advised to have lower fat diets and red meat and to increase their fish intake. Trans fats will increase the amount of cholesterol in the bloodstream, can increase the risk of developing coronary heart disease. So you want to limit your trans fats. And what they mean by trans fats is, if you look at this structure of this double bond here, if you remember going through this, these are on opposite sides. And so this is a trans double bond, and these are your trans fats. And that is shown here. This particular type of cracker does not contain trans fats, but it does have polyunsaturated fats. So there might be some where you have more than one double bond in your fatty acids. Foods rich in saturated triacylglycerols are fatty red meats, cheeses, and butters. Also fried foods and ice cream, because that's made of heavy cream. Food that's rich in saturated triacylglycerols just means that there's no carbon double bonds in the chain. These are solid at room temperature, and they increase your blood cholesterol level, while foods that are rich in unsaturated fats, such as plant oils, nuts, soybeans, and fish, these have one or more double bonds in the carbon chains. So we can see that here. They're liquid at room temperature, and they decrease our blood cholesterol level. And then we have foods that are rich in trans triacylglycerols. So margarine, many processed foods or fried foods, and even some baked goods. And these have one or more trans double bonds and are semi-solid at room temperature. These also increase our blood cholesterol level. And the way that trans fats are formed is they'll take a polyunsaturated fat, which has many carbon-carbon double bonds. So we're going to use some reducing reagent, kind of like H2. So let's say I had 4 carbon-carbon double bonds in my chain, and then I'm going to partially hydrogenate it so that I get only maybe 2 carbon-carbon double bonds. And when you hydrogenate it, and then your carbon-carbon double bonds become trans double bonds in the process, because that's a more stable one.